All right, in this video, I'm going to be talking about the logistic differential equation. And this is very hot right now. Does anybody know where I'm headed with this? The coronavirus. That is correct. Yes, I cannot estimate how many total cases there are, but I could describe to you how a person would. Okay? So, first thing, really, in this course, there's actually only 3 things we have to know about the logistic differential equation. Okay, we need to know, first, the shape of the graph. So I guess I'll just write shape of the graph. Okay, this one, I think a lot of people are familiar with this type of curve because you've seen it sometimes in like AP Biology or AP Human Geography or, no, it's not a bell, or maybe environmental science, because this shows up everywhere. If you studied economics to a higher level, you would see, in finance, you would see this type of thing as well. It is the most applicable thing that we do in this course, outside of, the fact that all of the derivatives and integrals and differential equations are really what the engine that powers physics. This is extremely relevant. Okay, so the shape of the graph, basically, it's an S. Usually. So what it looks like is, it kind of comes in, it starts off somewhere, and it goes, and then it levels off. Okay, looks like that. That is provided, I'm going to define some stuff. I'm going to call this this Y level here L. And this is the limit of the population. This is generally population versus time, but not always. L is what we would call the carrying capacity. And I'm going to call this P0. Now, P0 is actually something in our initial population, not actually something we have to worry about, but if you did take this a step further and actually solve the differential equation and find the solutions to it that generate that curve, you would need to be interested in the initial population. That's the shape of the graph. Now, and this is, this shape would be, suppose I've got a large, lush field. It's a field that has lots of grass and plant life and maybe some insects and not very many predators, and I dump in, say, like 8 rabbits. Okay? We know that as time goes on, I'm going to have more rabbits, but I can't have just exponential growth of rabbits because there's only finite resources. Okay? And eventually, my lush green field has some sort of carrying capacity for rabbits. And as we approach that, if I got too many of them, there would be competition for resources, there wouldn't be enough food, it would be bad. Okay? And provided that P0 is less than L, we will see this S-shaped curve. Now, I do have to mention what happens if P0 is greater than L, if we start out up here. This is if I take, I've got a forest, but it's not a huge forest, and I have it completely contained. I've got some prey animals in there. I've got, some honey and stuff like that. And I dump in, say, 10,000 bears. Okay? That's not going to work, right? In a very contained area, that's too many bears. Okay? They will not get along. There's not enough food is really the main issue. And so there will be some die-off here. And it will approach this horizontal asymptote the same way. Okay? And that is the other thing that can happen. So it just kind of looks like the graph of 1 over x. It just kind of decays. Yes?
Would it cross it and then would you approach it?
It definitely, in real, actual simulations, or actually in real life, if you study these things and track populations, yeah, it going up and then actually bumping over and then coming back down, or the die-off and then some regeneration. Yes, absolutely. Okay. And the second thing I need you to know is the form of the differential equation. Okay. Okay. This is where they write it as the rate of change of population with respect to time is given by some number times the dependent variable times some other number minus the dependent variable. K times P times L minus P. Okay, it doesn't always look like this, but really what it is it's got a linear and a negative quadratic term in the dependent variable. So, but it isn't always dp dt. It could be dy dx, and we're pretty familiar with that type of differential equation. So I'm going to write that as well. So that would be k, dependent variable is y, times L minus y. And again, they don't always write it as L minus y. It could be looking like 1 minus y over something. And we'll look and see a couple problems like that, because I have seen that a couple of times. Okay, that is the form of the differential equation. The third thing that I need to tell you is basically a trivia fact. And I'll show you why this is true. It's very easy to see why this trivia fact is what it is. But say the maximum growth rate Does anybody see where the curve is going to be the steepest? Like what's the pattern here? Yeah, okay, it's a point of inflection. I will come back to that, definitely. But how would you quantify it? Notice this is kind of the p-axis and this is the t-axis. I've given you nothing on t. What do you have?
It would be L over 2.
Yes, it's half the carrying capacity. And it always works like that. And the crazy thing is, I mean, you definitely could put a point of inflection wherever you want it, but if you just kind of draw this thing trying to make it an S, you always end up putting that point of inflection right at the right spot, right at L over 2. At half the carrying capacity. At P equals L divided by 2. And I'm also going to mention that there's a point of inflection there. So, I've got a question over here. Yes.
So could you use point of inflection to calculate like the max?
Yes. Okay. And so I'm going to start actually talking about the spread of infectious disease now. So the question was, is this kind of a tool that they would use to estimate, where we're at in terms of epidemic spread? Yes, absolutely. And I will be more specific about that. For those of you watching at home, I'm going to link a video in the description that is far more detailed than this one about the specific thing happening, right now, March of 2020. It's a 3 blue 1 brown video. It is great. It has got better animations than I could ever do, and it's got really good explanations. So look for that in the comments. I mean, not in the comments, in the description of the video. But what I'm going to say is that the thing is that if you look and all you see is this, you're going to assume that you are at the beginning of an exponential situation. But in our finite universe, exponential is really not possible. Okay, if you look at, as of the past, week or so, and you track the number of cases each day of the coronavirus, it looks like it's increasing by about 20% per day. Okay, and according to that model, in 5 to 6 months, I ran this yesterday, you get into the 11 cases. And the problem with that is there aren't 10 to the 11 humans. So this is somehow not really feasible as a model for, the spread of infectious disease. And that's kind of one of the classic, fallacies of human logic, is looking at something in the short term, extrapolating out, and thinking, hey, I'm at the beginning of an exponential curve. When in fact, you might be right here at the inflection point, and it's about to really level off. Okay, and you can see how that could be relevant to economics or business. And in fact, and this is usually the example I use when I talk about this, is about Samuel Walton. And you know about Walmart. Okay, I know we don't have one out here, but you're familiar with the concept. A place where Americans go to buy things, and there's all sorts of other stuff that happens there too. But at first it was just kind of like this regional chain of, grocery stores that might have sold some other stuff, to my understanding. This is how it was explained to me. And at that point, this is, 50 to 100 years ago, whatever, sometime ancient to y'all. The prevailing way of tracking sales and analyzing your business was actually filling in a book your, say, weekly sales of a product. Okay. And the thing about Walmart is they said, well, we're like, everything's always on sale. And, what Mr. Walton did, he made this discovery, and to my understanding, he was not highly educated in mathematics. He kind of just discovered this on his own. And what they would do is they would track the change in sales week on week. And what he started doing was he started looking at the second difference in sales. And this was particularly useful to fad items. Because as y'all know, there's got to be someone out there sitting on like 2 million fidget spinners, right? They just bought them right as it was starting to wane in popularity. Okay? And for fad items, this is particularly true. You can see how the total number of sales is going to really skyrocket, and then it levels off, and then nobody cares anymore. What he did was, especially for these trendy items, as soon as he saw the second difference go negative, that was when he stopped buying and just sold off the rest that he had. Okay? Which prevented them from having all this extra product sitting around that they had to discount and put on sale. That's why people used to put stuff on sales, because they had too much of it and they couldn't get rid of it, so they just lower the price. Hopefully people would buy it. That's why everything was always on sale. And if you think about the second difference, in our context, that's related to the second derivative, look, right there is where the second difference is going negative. Now, in terms of the spread of infectious disease, what you can do is you can look at the increase in new cases. And when the increase in new cases stops increasing, and it's like constant, that's evidence that you're right at about here. Okay? And then it will actually start, the rate of increase will start to decrease, and then it's starting to level off. So once you see, I forgot what it's called, it's maybe growth factor or something, it's a ratio. Once that hits 1, that's generally, they're going to say you're probably going to have about twice that many total cases. But the thing is that we haven't gotten to that point yet, so we don't know. And a lot of it has to do with, and again, I'm plugging this 3 Blue 1 Brown video because he's talking about the actual factors that play in, but there's a number of things that can, if you tinker with them, it can really affect the nature of the curve. And, some epidemics have a very low carrying capacity because they're actually not that infectious. And some, like the Spanish flu, was very contagious and ended up with a massive number of cases. I believe it said 513 million cases, which was over a quarter of the world's population, around World War I. And you all have heard about this in your history class. Okay, so I think, I'm sure I'll have more to say about, the actual meaning in the world, but for now I'm going to jump back to the map, and I'm going to show you why this is true. Now, this is not, I'm going to make a graph here, and it's not going to be a graph you're going to be very familiar with. I'm going to plot dy dx versus y, basically. So I'm going to, except I'm going to call it population and time, right? So I'm going to graph dp dt versus p. Okay. And now I know the form of the logistic differential equation is number times p times L minus p, where that L is that carrying capacity. And what I'm going to do is I'm going to actually distribute this out. So I'll have kpl, which is the same as kl multiplied by p, minus kp squared. So if we're graphing this as this is y and p is x, well, it's going to be a downward facing parabola, right? And moreover, from this factored form, I can see that dp dt equals 0 when p is 0 and when p is equal to L. Okay, so I'm going to actually mark those on my graph. Okay, p equals 0 here. P equals L, I'll say that's right here. Okay, well, I know it's a downward facing parabola, and I'm pretty good at graphing these. And you can see, based on our intuition about the symmetry of parabolas, that this vertex is happening at half the carrying capacity. You could also take the derivative of this with respect to p and find out where it's 0. Okay, and you would find that it happens at L over 2. I'm not going to actually perform that for you because I don't think that's going to really add any value, because I know that, you can get the result of the vertex happens at x equals negative b over 2a just by taking the derivative and setting it equal to 0. What I want to say is, if the derivative, which is dp dt, if the rate of change goes from increasing to decreasing, what do I have right here on the graph of the original? A point of inflection. You have a maximum in dp dt, but a direction change in the derivative indicates a point of inflection on the original, which is why, again, we are seeing a point of inflection at half the carrying capacity, okay? Because of the form of the differential equation. Here we go. All right, so let's do a quick example. So this one is from the, selection of College Board questions. There's the moose population, and we're going to call it M of t. It satisfies the logistic differential equation. dm dt is 0.6 times m times 1 minus m over 200. What is the limit as t approaches infinity of m of t? The first thing, before I even get into the form of the differential equation, I'm going to talk about, what does this actually mean? What are they getting at? What are they looking for here? Yes, L. They're looking for the carrying capacity. Bless you. Okay, so I need to just point that out right off the bat. Okay, now the thing is, this is not in our recognized form. dp dt is number times p times number minus p. Because I got this divided by 200. So what am I going to do? Yeah, I'm going to factor it to make it look exactly like the one I'm familiar with. But you're probably only going to need to do this once, because then you'll be like, oh, I get it. Yeah, I'm just going to say, okay, let's go over here. And I believe that this form may be the one that the Larson textbook defines the logistic differential equation as, is number times dependent variable times 1 minus dependent variable over some special number. But, we'll get there. So what I'm going to do is I'm going to say that this is equal to, and I'm going to factor out 1 over 200. So basically, if I factor out something, I'm dividing both of these things by it. So 0.6 divided by 200 times m. And if I'm dividing by 1/200th, I'm really multiplying by 200. So I'm going to multiply that by 200. I'm going to multiply that by 200. And you could check. If I distribute the 1 over 200, that'll be 1 and 1 over 200. So now what is the limit as t approaches infinity of m of t? Oh, don't everyone say it at once. 200. Yeah, 200. There we go. Okay, so if we know the form of the differential equation and know what they're getting at, this is the type of multiple choice question that we can solve in 10 seconds. Okay? And if we can solve this one in 10 seconds, that's 1 minute and 50 seconds or 2 minutes and 50 seconds we can spend on a hard question. Okay? That's what I'm trying to tell you, is that the multiple choice questions for logistic differential equation are oftentimes trivia facts that if we know, we can solve very quickly. Okay? So that's one type of example we've got. Oh, wait, question over here? Okay, so question was where specifically did I pull that from? And, oh, you can't see that, you can't see my mouse. I got this 200 from right here, because remember, the form is number times p times the carrying capacity minus p. So that means that this number is the carrying capacity. It also means that if you see number dependent variable 1 minus dependent variable divided by something, that's also going to be the carrying capacity. Okay. So I'm just extracting that number, making that choice and moving on with my life. All right, here's another example. This is a multiple choice question, another one. And it's which differential equation could fit the curve? Okay? But the thing is this doesn't look like... So what I need to do is I'm going to need to factor these. But I don't want to have to factor all 4 answer choices. Okay, so I need to eliminate a couple of them. Which ones can I eliminate right now without doing any factoring? C and D. Why, though? Yes. Okay, well, It wouldn't really matter if p squared was in front if it was negative. Yeah, it's the fact that I need this to end up being a downward-facing parabola, the differential equation to be a downward-facing parabola in p. So I'm going to say this is, both of these have the issue where the p squared has a positive coefficient. That's just not going to work. I need a negative number in front of the p squared. Okay. So I'm not considering those anymore. So it's much easier to just factor 2 things than to factor 4 things. You know what I mean? But then it's like, okay, y'all been in my class for a long time now, and you know that I am prone to arithmetic errors. And I'll tell you that I'm particularly prone to arithmetic errors when I'm working with decimals. So what should I do here to make this easier on myself and less likely for me to make an error? Make it a fraction. That's exactly what I'm going to do. So I'm going to say that this is equal to 2/10 of p minus 1/1000th of p squared. And then what I need to do is I need to get it to be equals number times p times L minus p. So I need to get this second p just a p. So I want to factor out the 1/1000 from it. So that's what I'm going to end up factoring out, is 1/1000. And again, if I'm factoring 1/1000, it's like I'm dividing by 1/1000. If I divide by 1/1000, I am in fact multiplying by 1000. So that's, I'm going to multiply everything by 1000. 2000 over 10 p, I'm also factoring out a p, multiplied by, wait, hold on, what have I done? Yeah, no. I've done this completely wrong. Okay, forgive me, viewers at home. I'm not going to re-record this video just because of a major factoring error. Okay, definitely everyone agrees I have factored out a p from here. But what I'm also factoring out is 1/1000. Okay, and then I'm multiplying this by 1,000. So 2,000 divided by 10 is 200 minus p. That's still visible? Yes. Okay. What are we thinking? Are we thinking this has a good chance of being the answer?
Yeah.
Why?
Carrying capacity.
Yeah, the carrying capacity is 200. We get that from right here. I see that the carrying capacity is 200 from the given graph. Okay, let's see why this one isn't it. Do the same exact thing. Times, this will be 100 when I multiply by 1,000. Okay, this one would be if the carrying capacity was 100. Okay, there's a couple of other questions I'm going to just grab real quick that we're going to run through very, very quickly. And I'm just doing it from my binder, and so, you know, people watching at home, it might be a little blurry at first. I might have to refocus because I'm just pulling out my old binder. It's going to be pretty far back here. Yeah. Logistic differential equations. At risk of showing you something. Oh, I'm going to use this one for the test, I know. Here we go. This is a very typical kind of question. Which of these is a logistic differential equation? Maybe I'll zoom in a little bit so you can see them better. Okay, which of these is it? E. Yeah. What about C? What's wrong with C?
It's dy.
It's dy dt. It's dependent variable. Okay, so that's the one that, you know, especially as time went on, you could be tricked by that one. Remember, it's dependent variable. And I think I've got another one that's very similar to this right behind it. Yep. Number of antibodies in a patient's bloodstream increasing according to logistic differential equation. Which of these could be it? E, again, yes. Why not D, though? What's why? D looks like a logistic differential equation to me. Yeah, there's no Y on the outside. Yeah, okay, there you go. That's another one. And B also looks pretty appealing. Okay, so just make sure that we know the form. This one, no, I don't think I really want to do that. The rest of the questions that I'm going to ask are going to be on the homework, and they're all going to relate back to these 3 trivia facts. And that's what I'm going to wrap up this video with, is I'm going to go back to the beginning as I get this binder closed. It's quite a million pages. I'm going to go back to this original page. I'm going to say, remember these 3 things we need to know. We need to know the shape of the graph. We need to know the form of the differential equation. We need to know the special thing about what happens at half the carrying capacity. It's maximum growth rate and a point of inflection. And I'm telling you, the questions that they ask on the BC exam about logistic differential equations are very easy, but this is one of the deepest topics that we touch on in this course. And the study of differential equations and their relationships to the real world is a really, really nice field of study of mathematics, and it's one of the ones that I like the best. So hope you enjoyed the video. Hope it was appropriate for this particular year. But really what you need to do is you need to check out the problems I put out for homework 13-2 and just do them and see that it's really not that bad.